Hello everyone. In this presentation, I will discuss to you the infrared spectroscopy. Let's begin with the definition. Infrared spectroscopy generally refers to the analysis of the interaction of a molecule within the infrared light. It also deals with the infrared region of the electromagnetic spectrum, such as light having a longer wavelength and lower frequency than the visible light. The infrared spectroscopy concept can generally be analyzed in three ways. First, by measuring reflection, emission, as well as absorption. The major use of infrared spectroscopy is to determine the functional groups of molecules which are relevant to both organic and inorganic chemistry. Let's proceed to the principle. The infrared spectroscopy utilizes the concept that molecules tend to absorb specific frequencies of light that are characteristic of the corresponding structure of the molecules. The energies are reliant on the shape of the molecular surfaces, the associated vibronic coupling, and the mass corresponding to the atoms. For instance, the molecule can absorb the energy contained in the incident light, and the result is a faster rotation or a more pronounced vibration. Next is the regions of the infrared spectrum. The infrared spectrum can be divided into three main regions, which are the far infrared, mid-infrared, and the near-infrared, wherein the mid-infrared region is of greatest practical use in chemistry, but the near and far infrared regions also provide important information about certain materials. So let's begin with the far infrared region. Organometallic and inorganic molecules contains heavy atoms and have weak bonds. Therefore, the fundamental vibrations of these molecules fall in this region. The lattice vibrations of crystalline materials also occur in these regions. Next is the mid-infrared region. The mid-infrared spectrum extends from 4,000 to 400 cm and results from vibrational and rotational transitions. This mid-infrared region can be divided into two regions, which are the functional group region, which is the 4,000 cm to 1,300 cm, and the fingerprint region, which is from 1,300 cm to 400 cm. Take note, this region is the most useful for the organic chemist since most of the organic molecules are absorbed in this region. So under this region, we have the functional group and the fingerprint region. When you say functional group region, most of the functional groups present in organic molecules exhibits absorption bonds in the region 4,000 to 1,300 cm, hence this is known as the functional group region. In this region, each bond can be assigned to a particular deformation of the molecule, the movement of a group of atoms, or the bending or stretching of a particular band. Fingerprint region, on the other hand, usually contains a very complicated series of absorptions. These are mainly due to molecular vibrations, usually bending motions that are characteristic of the entire molecule or large fragments of the molecule. Take note, it is very difficult to assign individual bands in this region. Two molecules having the same functional group may show similar spectra in the functional group region, but their spectra differ in the fingerprint region. Therefore, Both the regions are very useful for confirming the identity of a chemical compound. And for the third region, we have the near-infrared region, which is generally used for qualitative analysis and studies of hydrogen bonding, solute-solvent interactions, organometallic compounds, and inorganic compounds. So the absorptions observed in the near-infrared region are overtones or combinations of the fundamental stretching bonds. Bonds in the near-infrared are usually weak in intensity. They are often overlapped and hence less useful than the bands in the mid-infrared region. So the IR spectrometer has five main parts, namely the radiation source, sample cells, monochromators, detectors, and recorder. So we will discuss the use and function of each. Let's start with the infrared radiation source. Infrared instruments require a source of radiant energy which emit infrared radiation. So this IR source must be steady, intense enough for detection, and extend over the desired wavelength. So various sources of infrared radiations are as follows. First is the Nernst glower, incandescent lamp, mercury arc, tungsten lamp, Glauber source, and the nichrome wire. Next part is the sample cells and sampling of substances. So the IR spectroscopy has been used for the characterization of solid, liquid, or gas samples. When you say solid, various techniques are used for preparing solid samples such as pressed pellet technique, solid run in solution, solid films, and Mall technique. Liquid samples can be held using a liquid sample cell made of alkali halides. So aqueous solvents can be used as they will dissolve alkali halides. Only organic solvents like chloroform can be used. Then for the gas, sampling of gas is similar to the sampling of liquids. Next part is the monochromators. It is used to separate the color components of a light. It can use either the optical dispersion phenomenon in a prism or that in a diffraction grating. Example of this are the prism, gratings, and filters. Prism are made up of potassium bromide, sodium chloride, or cesium iodide. Filters are made up of lithium fluoride, and diffraction gratings are made up of alkali halides. Next is the detectors. Detectors are used to measure the intensity of unabsorbed infrared radiation. Thermal detectors and photon detectors are used. So detectors are also the one that convert radiant energy into an electrical signal. Thermal detectors consist of thermocouples connected together to produce greater sensitivity, while photon detectors rely on the interaction of infrared radiation of a semiconductor material. Lastly is the recorders, which are used to record the infrared spectrum. So let's proceed with the instrumentation. As you can see in the picture, first, a beam of infrared light from the source is split into two and passed through the reference and the sample respectively. Infrared light now passes through the sample material. Then, depending on its energy, this can trigger the vibration of specific molecular bonds. That is why we need a fitting light source to be directed at the sample. Now, both of these beams are reflected to pass through a splitter and then through a detector. Finally, The required reading is printed out after the processor deciphers the data passed through the detector and can now produce a signal. So how to read result graph? So we have here the x-axis or the horizontal axis, which represents the infrared spectrum, which plots the intensity of infrared spectra. The peaks, which are also called absorbance bands, corresponds with the various vibrations of the sample's atoms when it's exposed to the infrared region of the electromagnetic spectrum. So for mid-range infrared, the wave number on the infrared spectrum is plotted between 4,000 to 400 centimeter. Next is the y-axis or the vertical axis, which represents the amount of infrared light absorbed or transmitted by the material being analyzed. So interpreting the infrared spectra starts at the high frequency end to identify the functional groups present. The fingerprint regions are then studied to positively identify the compound.